Oh. It's a weird angle record.
Well,
I'm not complaining.
if you want to be the camera, you can be promoted to a camera.
Okay, I guess we can start, no? It's 9:30, so morning everyone. So first speaker this morning, Edmond, and then we have a coffee break, I suppose, right?
It depends on him.
We have a coffee break anyway.
Whenever I finish.
The second one
Well, it's a
will be
friendly audience, so I guess we'll have the coffee break.
So one is not here anymore, so we have a car.
One is here in spirit.
So I'd like to thank the organizers, also the conveners, for allowing me to give a talk on a topic that doesn't seem very much related. You were just complaining yesterday evening to the main topic of this week. As a matter of fact, I like to convince you that there is some deep analogy between the form of jet quenching and that of PA collision. To some extent, the jet acts as an energetic dilute probe, which interacts with the dense system, in this case, plasma plasma, which may be viewed as a generalization of a large nucleus behind the shockwave approximation. And in fact, the formula which is used to study jet quenching, it's like a generalization of the choreographed condensates formalis behind the Acorn approximation. Now try to make this point of, few technical points of that kind, because the audience here is very much expecting that physics. So just to make these connections more explicit. So, well, I will start with a brief introduction to the phenomenology of jets in heavy ion collisions, the physics of jet quenching, the general problematic of jet quenching, and some examples like of observables like digital symmetry and fragmentation function. I like to convince you that there are essentially two types of radiation: vacuum-like, which is driven by the particle mutuality, which goes according to the standard Brainstorm law, and the medium-induced radiation, which is driven by multiple source scattering in the plasma, and goes according to the BDM-PSZ law. These two types of radiation are separate, well understood for a long time by now, and now I'd like to tell you how to combine them together with sympathic QCD. So I'll discuss them separately first, and then I'll show them formats that have developed recently in Saclay, which shows how these two kind of formats, the radiation can be factorized in QCD. Yeah, control approximations. So basic introduction, you probably know all that, but then we get back on this. So we look about the production of jets, which are generally produced via hard processes, giving rise to two hard partons. We can evolve via radiation, giving rise to two back-to-back jets. At least this is the case in a dilute environment of proton-proton collisions. In the context of the nucleus collisions, the jets are produced inside dense partonic medium, an expanding quark-gluon plasma, and because of that, the jet can interact with this medium, and they may interact differently because they're not produced necessarily in a symmetric point. So because of that, the final jets may be different from each other because they have interacted differently. They have propagated along different distances, they have seen different densities. And by studying the difference between the two jets, for instance, one can infer properties of the quark-gluon plasma. Well, just to remind you also what is the experimental definition of a jet. The experimental jets are defined by grouping together hadrons which propagate at nearby angles. That would be the situation for, say, a symmetric pair of jets. They're back-to-back in a transverse plane. They may have different notional momenta because they come from partners with different values of x. The opening angle, which is the experimental definition, is called German air. I would sometimes call it zero, doesn't matter. We have both S and air. And I will define two regions which are important for what follows. There's the region inside the jet and the region outside the jet. So any radiation outside the cone is lost for the jet. It's energy lost by the jet. And what finally counts, what's called fragmentation function, are just particles which propagate inside the core. And I will try to convince you that the major modifications refer both to the jets and to the outer region. So when the jet is produced in a quark-gluon plasma, both the inside distribution and the outside distribution is modified. Okay, so that's a typical event, with a digest event in proton-proton collisions. The jets are nicely symmetric and collimated. And that's what's called a monojet event in lead-lead collisions. In fact, once one jet, because the other one has lost so much energy that cannot be distinguished anymore from the background. The primary jet has like 100 GeV or more, what the secondary jet cannot be distinguished if the energy is below 25 GeV, because that's the resolution of the experiment for the jets. And that's another example, which is highly asymmetric, but this time one can see nevertheless the two jets, that's from CMS. One jet had like 200 GeV, the other one like 70. When these jets were first identified, this kind of asymmetric events were first identified, there was a lot of questions about where the missing energy. So there is no missing energy. By careful analysis of the underlying event, the experimentalist from CMS has found that the whole energy difference between these two jets is found in the underlying event as an excess in the energy in the hemisphere around the away jet. But this excess is now carried by many soft hadrons propagating at large angles. So somehow this jet, which has been framed by the medium, has been modified in such a way that it has produced, has been irradiated many soft hadrons at large angles, and that radiation pattern is quite different from the usual fragmentation pattern in the jet. I'll try to explain to you what is a natural explanation for this finding. Well, that's another way to look at the phenomenon of digit asymmetry. It is the event fraction as a function of the difference in energies, called PTs in the experimental context, I call it energies, because they're mostly as central activities. But the asymmetry function AG is a difference in the energy of the two jets divided by the sum of the jets, and that's an event fraction as a function of this asymmetry. First in proton-proton collision, and you see that most of the events are symmetric, but there is a large fraction of asymmetric events, so at 0.4, which is associated with radiation for two-jet events. But if no one moving to lead-lead collision with increasing centrality, one sees that the higher the centrality, the higher the proportion of digit events which are more asymmetric than proton-proton collisions. And for instance, if you look at the more central 10% collisions, you can see that the peak in the event distribution at asymmetries of order 0.4 instead of being at 0 in the case of proton-proton collisions. That's again a way to quantitatively measure in a statistical way the importance of digit asymmetry. Good. Another kind of nuclear modification is what's called the nuclear modification factor for jets, which is the ratio between the yield of jet in lead-lead collision divided by the yield of jet in proton-proton collision, normalized by the nuclear symmetry functions. It's very similar to what we know from the RPH quantity and also for RAA for hadrons. So this time one measure the jet production. And what I showed here is some data from our class showing this RAA for different centralities increasing in this way. You can see at the most central events, you have pronounced suppression of jet production in lead-lead collisions, which essentially becomes flat at high PT of the jet. So up to 1000 GeV, at 1 TeV, the jet is suppressed strongly, and the approach to activity is very, very slow, if any. And I will explain to you later that, that this suppression is naturally interpreted as a consequence of energy lost by the jet inside the medium. A simple explanation, I mean, a simple way to understand that, but I will return later, is that to remember that the production, the hard procession production, the production for jets is rapidly decreasing, the procession is rapidly decreasing with PT. And if there is a little bit of energy loss, the jet shifted, the spectra shifted towards lower PT. And then since the procession is rapidly decreasing with PT, the fact that we measure as a given PT jets coming from higher PTs makes a strong suppression. And that's the kind of mechanism which naturally explains the RAA suppression. The fact that RAA is almost flat at high PT, I will tell you later, it has to. So first of all, it shows that the energy loss increases with PT, because if the energy loss was a constant quantity, then the effect of the energy loss should be less and less important in increasing PT. So the energy loss increases with PT, and I will explain that later to you, that has to do with vacuum radiation. And the final observable that I would like to focus on, there are many, but I will not have the time to discuss all of them, what is called the jet fragmentation function, which is the energy distribution of the hadrons inside the cone axis. The jet cone, in this case, inside the jet of area 0.4. So that's again, the spectrum is omega again by d omega, as obtained by integrating the two-dimensional distribution in angles and omega over all the angles in zero air. What is called PT again for me in that case is the energy omega of a hadron inside the jet. And what's called PT jet is the energy of the leading particle, the whole jet in this case. So the whole jet is a single particle. And that's the ratio between the fragmentation function in lead-lead collision divided by proton-proton collisions. There's an interesting structure which emerges. You see that there is a slight suppression in the fragmentation function at intermediate energies around 10 GeV. And there is a strong enhancement in the distribution of softer particles in lead-lead compared to proton-proton. And also a slight enhancement at high BP, at large values of the STT fraction there.
Sorry,
yes.
So usually fragmentation functions are functions of Z.
Yes,
or you can change the variables.
You can change the variables, and I want to show that the same pattern occurs when the distribution is plotted versus Z or versus B. For getting the vacuum versus Z is the only way which is meaningful because there is no difference. For getting the medium, there is an additional scale generated by the medium. So this may make a difference in plotting a function because they intrinsic scale. They are shown both. I mean, of course, the plots are not identical, but the shapes are identical. So the phenomena are identical. Okay, so far the various observers I mentioned to you express two classes of nuclear modification inside and outside the jet cone, and I will argue later that they refer in fact to different types of radiation. So now I will start describing the evolution of a jet in the presence of a dense medium. So that's supposed to be a hard event here, which creates due to the scattering, which creates a hard parton. This one, I don't want here, I only follow this one. And this parton is virtual, so it evolves via radiation, via branchings. And in case there's a medium around, it also evolves via collisions of the medium constituent. It's clone and change the T channel. So the leading parton and also the products of the fragmentation can interact with the partons from the medium. And this collision can have several effects. They transfer, obviously, energy between the partons in the jet and those in the medium. They trigger additional radiation for medium induced because even if this particle is on a shell, because of the scattering, can acquire enough sharpness, it's accelerated. And they're also importantly, they wash out the color coherence between the say, antennas created by the branchings, which will be coherent in the vacuum, but now they get scattered in the medium so they can destroy the coherence. And that has consequences for the interference factor. I will describe all that. So the simplest consequence of the collision in the medium is the exchange of stranded momentum between the medium and the partons, which brings a browning of the distribution of the partons in stranded momentum. If you look only at the leading particle, it started having, by definition, stranded momentum will be equal to 0 because I set the launcher axis along the jet, along the leading particle. But then this collision gives rise to a browning in the same way as we have browning in the stranded momentum when you look at quark production or gluon production in PA collision. The same physics, and the mathematics goes the same way. So that's the cartoon which describes the physics type of direct amplitude and complex conjugate amplitude. So I have a quark in this case which propagates along the medium over a distance, a LiPo distance L. It starts with a stranded momentum perturb, equals 0, and ends up with a stranded momentum perturb coming from momentum browning from collisions inside the medium. And as usual, I can describe that in the equal approximation. So it's useful to also describe the quark having a fixed stranded kinetic spur. So as soon as this quark is energetic enough for the stranded momentum browning not to modify his stranded velocity. So I assume also that the medium is quickly coupled. It's a Brownian plasma at high temperature. And because of that, these different partons here can be viewed as independent scattering centers. And because of that, the scattering of these independent, the multiple scattering of independent sources introduces random kicks in stranded momentum, leading to a random walk in p-part. So the average p-part squared increases proportionally with the medium size L to with a proportionality coefficient, which is a transport coefficient known as the jet quenching parameter. And I will show now how this comes out in a more mathematical way. So as I just mentioned before, the scattering can be computed in the acorn approximation, which means that the quark wave function is only modified by by phase, by colorization, which depend on the standard coordinate expert, and which involve the color field in the target, which is the color generated by all the thermal constituents of the plasma in this case. And there are two such Wilson lines, one for the direct amplitude, one for the colorless colligated amplitude. There's a sum of the colors in the final state, average of color in the initial state, all that makes the color color diagram. Exactly that for PA quality. So this mathematical analogy shows that one can compute the cross section for the time momentum Browning of the quark as a Fourier transform of a mathematical dipole, maybe students online, average over all the color sources or color fields in the target. And for a weakly coupled plasma, this average is Gaussian, so you were exactly in the setup of the MV model. If you want, the two-point function of the color fields in the plasma is local in a lifetime time of the rapid moving quark by Lorentz contraction. It is a Coulomb field, so it has a K1 or K force, which is screened at large distances by Debye screening. Because we have a plasma here, we have moving charges, so the polar interactions are screened over distances of the lambda or the inverse of the Debye masses, so for the alpha s and Debye is for the GT. And M here is a density of charge constituents in the medium, quarks and gluons, weighted with the color factors, and it goes like the cubic power of the temperature for gluon plasma in thermal. So that's exactly like the MV model. We have, instead of having valence quarks, we have thermal quarks and gluons with a density, and that's a Coulomb potential for the scattering between the probe and the constituent.
So this is assuming some local device screens also.
I mean that's PQCD. In PQCD, you start with the ideal quark-gluon plasma. But this ideal leading body, if you have this ideal picture, we have no interaction. If I modify the screening phenomena, which are leading body phenomena at large distances. So it's the leading body picture of PQCD, and the delta function appears because of Lorentz contraction.
I guess the power counts in, right? In the nucleus we have A, the atomic number.
Here we have the TQ.
Here it's
the temperature.
But really just n the number of sources because of high temperature.
Exactly. Right? So then the subsequent calculation of the expectation values of the Wilson lines go exactly like in the MV model because mathematics is identical. So you get an expectation value of the mathematics. I put the index here because that's still an approximation of the evolution. It's an exponential of a momentum squared scale, which is proportional to the medium length L times the coefficient, which is proportional to the density, and which involves the transport cross section, so the integral over the over Coulomb potential squared multiplied by k squared because we need a k squared factor to weight the scattering in order to achieve a final picture that we want to measure. So that's a standard cross section, transport cross section, and we proportion also with n and g force of the scattering here, and because of the g squared here. So g squared from there and g squared from there. This integration here is logarithmic, so it is cut off at the Debye mass in the infrared, and at the scale of that at which we measure the gluon distribution in the target, which is an inverse dipole size. So it depends logarithmically over the inverse dipole size, and I write it here as q squared plus 1 r squared. And that's a leading order approximation for the jet quenching parameter. Now if you perform the Fourier transform of that to get the distribution of the quarks, then the first approximation is the Gaussian integration. So it gives you a Gaussian distribution with an width, which is traditionally called in the holograph picture the surface momentum of the target. In this case, it is L times Q0, evaluated itself at the scale QS, so it's a slightly implicit equation. And that's confirmed the fact that the average value of P squared have given by this distribution. It's linear in L, and this is the value of transfer coefficient. Linear proportion with the density. So it's called the alpha squared times the TQ up to the law.
When you say Q naught is evaluated at Q squared, you don't need the running of the coupling, you just need that one law.
I will also speak about running of coupling. For the time being, no. For the time being, it's fixed coupling. But in a moment, I will also reduce the running of Yeah, for the time being, but the running of the coupling also will be at QS. But that
from my calculations, one of these two couplings would run with QS, the other one would run with some infrared.
I fully agree. What I mean by the one of the running here.
Yes. Just under.
That's yes.
So why is the cross section for ED broadening as a Gaussian, not a power mode? You have the law.
That's what I showed here. So there are two situations. It is a complicated function just because of the law. We cannot make a Fourier transform exactly. But there are two situations. One is the typical one in which you look at people of the order of Q-sat or smaller. In that case, the integration over R is cut off by the Gaussian. It's cut off at the R such that the exponent becomes equal to 1, because the integration would like to live as far as possible at R as large as possible until it's cut off. And then, for the purpose of computing the integration to leading log accuracy, one can replace 1 by R by QS. On the other hand, if you insist in looking at people much bigger than QS, that's your choice, then automatically the integration will be cut off by the phase here. And then at distance R much more than 1 by QS, then you can expand the exponential like here. And then the Fourier transform of the logarithm is the power on QS. Okay, so I have the spectrum has two distribution, two characteristics. It has a Gaussian characteristic at people of all the QS up to QS, and has a tail 1 on people 4 at people much bigger than QS. In fact, they're both going to play a role in both.
Yeah, it's not like so. The interpretation of PT squared as average.
Yeah,
it's misleading, right? I mean, because of the tail.
Right. So this is the part given by, so this is a typical value. This would be the average value if one only averages over the typical element.
So it should be PT squared. No,
it's 54. It's 54. The scattering is that's Coulomb scattering. It's not the Coulomb distribution. What you call the Coulomb distribution is P per square times the Fourier transform. Right? So what you call in color glass picture, the anterior Coulomb distribution is P per square times the Fourier transform. And that one those are quantities. But here I don't care about the Coulomb distribution.
That Fourier transformation.
It's one.
It's a long time.
It's an R squared here. It's a long times R squared here. Okay, that makes the one be fast.
So the dimension.
It's D to R squared. So
just because upstairs also you have the dimension is different from the L is missing. The L is missing.
I forgot the L.
Yeah, that's right. Yeah.
Sorry, I forgot the L. Sure. Yeah, that is very important. So in the cross section is proportional to a single scattering, and the scattering can occur anywhere, so it's proportional to L. So n is T cubed times L makes the dimension 2 divided by 4 makes the dimension minus 4. Sorry, and here is minus 5. Good. Okay, so far I discussed momentum rolling at sea level. Now I move to the fields of radiation, then I'll return to momentum rolling at the INT level. So radiation. Well, would be important what follows to keep trace of the formation time for radiation. So I remember briefly the argument for the formation time. So by the uncertainty principle, it takes some time for a gluon to be emitted by a quark. And that's a time over which the gluon and the quark separate from each other over a distance in the transverse plane, which is larger than the transverse wavelengths of the gluon. So the transverse wavelength of the gluon is 1 k per, which is essentially 1 over omega theta, where omega is the energy of the gluon, which is the opening angle. The formation time is given by the condition that the transverse separation at the formation time, which is theta times delta t, the formation time, be larger than lambda per, which is 1 over omega k per, 1 over omega theta. And this requires this delta t to be larger or equal of this scale, which is the formation time, which is omega over k per squared, or equivalently 1 over omega theta squared. So that's essentially the time it takes to emit the gluon. And this argument is just uncertainty principle. It applies to both vacuum-like and medium-energy radiation. So long as we're looking at vacuum-like radiation, this formation time is essentially measured from the hard scattering. So if there's a hard scattering somewhere here, the gluon can be emitted anywhere within this time as measured from the place of the hard scattering. Whereas if you look at medium-induced radiation, which is triggered by collision, this formation time is measured from the collision time. It can be anywhere inside the medium. And so I will have this both situations. So now I move to medium-induced radiation. So I have, I consider the possibility that gluon, say, split into two gluons, or radiated gluon, because of the scattering of the medium constituent. So these collisions introduce a lower limit on the transit momentum of the radiating system, because during formation time, the radiating system acquires at least transit momentum squared, which is Q-head transformation time. So since K per squared must be bigger than that value, could be much bigger than that, but could be also cannot be smaller than that, because that's what it is acquired during formation. So since we have a lower limit of the time momentum squared, and since that momentum squared enters in the denominator of the formation time, this introduces an upper limit of the formation time. So when we create particles via radiation inside the medium, the formation time cannot be larger than this quantity here, square of omega divided by Q-head. This upper limit comes by just replacing K per squared by Q-head times Tf and then solve for Tf as a function of omega. This applies to emissions which occur inside the medium. So one has this constraint so long as the formation time is more than L, and this introduces an upper limit on the energy of the medium-induced radiations. One cannot emit gluons with energy omega bigger than omega c, which is Q-head L squared. When Tf is L, this gives Q-head L squared. And that scale omega c will play an important role. So at this level, I can distinguish between three types of emissions. There are, first of all, vacuum-like, or as described by usual Bremsstrahlung. They have a transit momentum squared much bigger than Q-head L, or if you prefer, a formation time much more than square root of omega squared. And their probability is given by the Bremsstrahlung. In the same kinematics, I can have also medium-induced radiations, which are triggered by a single half scattering. This half scattering gives a high transit momentum, much bigger than we had there. Exactly like I was discussing here. It's much bigger than this. So it means that these medium emissions also occur very fast, but they have a different probability law for the emission, which is very similar to the law from here, and which is not Bremsstrahlung. And finally, there are medium-induced emissions which are triggered by multiples of scattering, for which the transit momentum of the particle at the formation time is precisely given by the multiple scattering, meaning that the formation time saturates the upper. And all these radiation plays work all my follows, especially the first and the second. But the second one is also interesting for computing radiative coefficient to Peter Browning. So before I had a quark which undergoes multiple scattering in the medium and acquires a transit momentum because of the scattering, but this three-level process can be modified by radiative corrections, by the emission of a gluon in this case, that emission of the gluon in the direct amplitude, which is on the reabsorbed complex conjugate amplitude. That's a real correction because the gluon exists in the final state. That's a virtual correction of the gluon is emitted and reabsorbed in the amplitude, which is also similar to the complex conjugate amplitude. And these gluon emissions give rise to a recoil. So if the gluon takes momentum K per, the quark has momentum minus K per, and this recoil also modifies the transit momentum distribution of the quark. So it contributes to momentum Browning. A priori, this is a higher order effect because we need a power alpha s to emit and reabsorb the gluons. But I will show in a moment that these emissions are amplified by logarithms, and this gives rise to evolution equations. And in fact, there are leading order effects. Yes, the emission of the quark, sorry, the emission of the gluon by the quark can be computed in the equivalent approximation, in the sense that the emission vertices are equivalent. On the other hand, I'll show you in a moment that, let me explain now, that on the other hand, the propagation of the gluon during the medium cannot be computed in the equivalent approximation because the gluon undergoes scatterings all the way during his lifetime, or formation time. So I remind you that the scattering can be computed in the equivalent approximation provided the transverse deviation during the collision time remains much more than the transverse wavelengths of the gluon, in this case, 100 K per. But this requires that the duration of the collision be much more than the formation time. But in this case, the gluon scatters all the way during the formation time, so delta T is Tf, and because of that, this condition is not satisfied. So one cannot use the equivalent approximation for the propagation of the gluon, but only for the emission vertices. That makes the problem more complicated. This being said, there is, in principle, a formalist allowing you to write the final rules for these emissions and for real terms and virtual terms, and one can write the analog of the BK-Chimock equation, which reassigns kind of information to all orders. But it's a complicated equation because, in fact, the scattering can be described by path integrals, which take into account the transient diffusion during the propagation during the formation time. So it is not the equation which are formal cannot be solved in general. However, if the purpose is to compute the main effect of these emissions on the transient momentum Browning, the equation of momentum, to Browning, then the mathematics becomes much simpler because, as observed by our collaborators a few years ago, the dominant radiative corrections are associated with fluctuations which live short enough to undergo only a single scattering. Why? Because those fluctuations precisely have a power spectrum over 1K force, so they have a tail at large K perp, and this tail at large K perp permits by recoil a large K perp Browning for the emitter. Whereas the medium-induced radiation, which has larger lifetimes, would have only K perp of all the saturation scale during formation time. So the condition for having single scattering is that these gluons here have a formation time much more than square root of omega of Q hat. This omega and Q hat reflect omega different the gluon energy. And for such gluons, the spectrum, the radiation probability is given by the standard Gunion-Birch formula. So it is like a Bremsstrahlung in energy, but you have a 1 over K per 4 tail times Q0 Q hat times L. This describes the single scattering from here. So this emission is triggered by a scattering which can occur anywhere during the medium, because this gluon can be emitted and reabsorbed. It has a short lifetime, but can be emitted and reabsorbed anywhere inside the medium. So the spectrum is amplified by a factor L because of that. And the Q hat describes the probability for the local scattering. And there is this power of tail because it comes from scattering. So this being the spectrum, one can easily compute the contribution of this radiation to the recoil of the incoming quark. One just has to integrate the production cross sections for the gluon production over all the energies and K perp of the gluon with a weighting K squared, because this is what contributes to the percent of the K perp taken by the quark by recoil. And you see, because the spectrum was 1 over K perp fourth, after weighting with by K squared, it becomes 1 over K perp squared. So we have a logarithmic spectrum enhancement in K perp. And of course, there is also logarithmic enhancement in energy, standard Bremsstrahlung. So altogether, we have radiative contribution to the P perp Browning of the quark, which contains a double log, an energy log, and a fundamental log, which is not a standard fundamental log from Bremsstrahlung. It comes from a scattering Bremsstrahlung, but because of the weighting K squared. And this gives a change. See, the change P perp squared is proportional in L, and hence can be described as a change in the Q hat, delta Q hat, in the jet wedge parameter. Now, what is better non-trivial in this calculation is to set up the proper integration limits for the energy and K perp integration. For that purpose, it is more convenient to use the formation time and the K perp as independent variable. The formation time is defined in this context as square root of omega divided by Q hat. So in these new variables, the K perp squared has to be much larger than K type formation because it's constrained, and can be as large as Q hat L because that's a maximum transient momentum which is acquired by the quark while crossing the medium. And the formation time itself can be as large as L, and can be as small as the inverse of the temperature, with a minimal scale for a scattering between external particles and an external probe. So together, these two integrations give a double log, which happen to be a log squared because the integration limit match with each other. So the change delta Q hat due to one step in the evolution is proportional to the origin Q hat times alpha s times the log squared. And since alpha times log squared can be a big number, one has to assume that to our order, and one can do that by returning to the general analysis with real language operations, realize that in the limit of the double log enhancement, one can reduce the general decay equation in the medium to a linear equation which is down of the VLA equation. And that equation, it looks like the standard VLA, but it has medium-dependent integration limits because of we have here and medium size there. But still can be solved exactly. It gives this Bessel function general with a VLA approximation, and at large logarithms, one can use the asymptotic version of the Bessel functions, and this shows that Q hat of L has an anomalous dimension. So Q hat depends upon L not just in a logarithmic way, as was the case at tree level, but now it depends upon a power of L, which happens to be the square root of alpha. The square root of alpha is typical for the VLA approximation. And that is the large anomalous dimension because this downward to the 1 for alpha is 5.25. But this is not the end of the story because at this level, running coupling effects are important. We know very well whenever we speak about big lab physics, and VLA is like big lab physics, the running coupling effect of order 1. So together with Dionisio, we managed to put the running of the coupling, as Julius mentioned, this running only enters 1 power of alpha s, two of them, and with running depending on the caper, which is the caper, so it's taken by the gluon here. With this running, this equation can be solved, not analytically any longer, but can be solved in a series expansion, which can be as precise as you want, and one can obtain the dotted curve here, which shows a slower increase with y than the fixed coupling. And in particular, the increase of the logarithm of Q hat at large, the medium size L is not linear in the logarithm of L, but is square root of logarithm of L. So it's slower than the Q hat the function of L increases slower than an exponential. That's again typical for the VLA approximation of running coupling. Okay, so that was the discussion of the momentum broadening and of the relative correlations to it associated to this kind of Punion-Birch or GLV radiation, in which the gluons emitted are hard enough to be emitted via a single hard scattering second. Now I will turn to the more important case for my purposes of the radiation produced by multiples of scattering. Why is it important? Because we like to compute not just momentum broadening, but also energy loss. And the signal hard scattering does not control the energy loss. Because if I take the Bunion-Birch spectrum here and I integrate over omega and k with a weighting factor of omega, so I don't compute the contribution of this radiation to energy loss, then one loses the logarithmic enhancement in k curve. So one sees right away that the k curve integration is always dominated by the lower limit. It means it's dominated by radiation with k per squared of order Q hat time formation. And when this is the case, then we're back to the regime where the radiation is triggered by multiples of scattering. So for that radiation, the calculation of the spectrum, not the calculation here, was given by people here, our collaborators, and also Zaharov independently, and that's the initial spectrum. So this is replacing the Braunschweig spectrum, if you want, and also replacing the Bunion-Birch spectrum, and it's different. It's different from all of them. They know no logarithm in energy, no logarithm in time either. So what is the spectrum? Well, it's an alpha bar. There is a factor L divided by the formation time given by this function here, which shows the fact that the emission can occur anywhere inside the medium. And that's an effective temporal phase for the emission. And then there is a Gaussian, which shows that the gluon is emitted with a transfer momentum k per, which is acquired during formation. So the width of the Gaussian k per squared is the same as Q hat times formation. And with this tau formation from here, we get Q hat times omega as well. So that's the kind of momentum broadening during formation. The gluon comes out after the typical time of this order, which depends upon the energy, and with the typical transfer momentum of that order, which also depends upon the energy. So the energy controls everything. And as I mentioned earlier, the formation time should be smaller than L, to mean that the energy omega here can be as much as omega c, which is Q hat elsewhere. I emphasize that because this will appear again and again. Now, so far I only discussed the radiation at the time of scattering. at the time of emission. So the triangular momentum here is acquired only during the formation time. But after being produced, the gluon keep propagating to the medium, so its transient momentum can increase via collisions after the formation time. So you see, this is a schematic of this kind of emission process. That's a quark emitting a gluon. There is a formation time, so not tau f, and then there is a medium size. So the gluon keeps acquiring transient momentum during formation and after formation. So because of that, his angle grows from the formation angle up to the final angle. So the formation angle is just the transient momentum at the formation time divided by the energy of the gluon, as this expression here. Notice that the formation angle, decreases with giving energy because this power here is bigger than power there, and so the minimal angle corresponds to the maximum energy, which is omega c. Okay? And this minimal angle is called theta c, which is the formation time for omega equal omega c. It will be also important what follows, but I have that. But this is not the final angle in general. This angle for here, because after being formed, the gluon keeps accumulating triangular momentum up to a maximal value of order Q hat L, because it propagates typical over distance L inside the medium. So the typical final angle for general energy is square root of Q hat L divided by omega, and this is the same as the minimal angle times the ratio between omega c and omega. So that's just a way to emphasize that soft gluons have large production angles, and they also have small formation time. So when omega is much more than omega c, the formation time here is much more than L, and the production angle is much bigger than theta c. And of course, some of these gluons will propagate at angles theta bigger than the opening icon of the jet, so they will be lost by the jet, and these gluons will induce energy loss by the jet. So the energy loss by a jet is associated essentially with radiation of soft gluon at large angles, larger than the jet opening. So now let me just complete on the energy loss as associated with the spectrum. I start again with the spectrum from here, but I integrate over K-per because I only look at the energy dependence. So that's the spectrum here. It's alpha times the ratio between the medium size and formation time, which scales like alpha divided by square root of omega. And this is value for omega smaller than omega c. Now, if we just compute the average energy loss by a particle's initial energy E, might be an omega c, which has to integrate to the spectrum over all the energies. And because of the power 1 over the square root of omega, the integral here is denoted by the upper limit, which is omega c. So one finds the result, which is over the alpha s times square root of omega c times omega c, which is alpha s times omega c. For alpha s, we have L squared. But so this average energy loss is controlled by hard emissions, the hardest possible emissions, which occurs probability for the alpha s, because when one omega is of order omega c, the probability is for the alpha. So they are rare events, but they take away a large energy. On the other hand, the energy taken by these emissions remain at small angles, theta c. Because I just mentioned that there is the smallest value of angles, theta c here, which is the angle associated with very hard emissions. So they are hard, they have small angles. So this energy typically remains inside the jet. So the average energy loss is not relevant for the energy loss by the jet because it remains a part of the jet. So it is irrelevant for the physical dijet asymmetry, not for all the typical events. On the other hand, if we look again at this formula for the probability, once that the probability for the emission becomes for the 1, we have typical emissions, when the energy is relatively soft of this scale omega branching, which is alpha squared times omega c, because we need this to go for the 1. That's a much smaller scale, but it's not that soft. One can use the typical value for alpha bar here and L to see that this scale here is about 5 GeV, so it's a semi-hard scale. And this kind of emissions, I'll argue in a moment, propagate at large angles, so they can take the energy outside of the jet. They can contribute to the energy loss by the jet. So since the probability becomes of order 1 when omega is of order omega branching, this means that in a typical event, the leading particle emits of a number of order 1 of going to omega of omega branching. Could be 1, could be 2, but not much bigger. On the other hand, this probability becomes much bigger than 1 when omega is much more than omega branching, which means that the gluon with energy much more than omega branching can be radiated abundantly, so they're very numerous, but they take only very little energy. So in fact, these numerous but soft gluons don't really matter. The gluons which matter are still those for the one with omega or for the omega branch. The angles made by these gluons can be easily estimated. You see, since the energy is omega branch is alpha squared times omega c, if you go to this formula from here, you see that the angle for this gluons is of order 1 over alpha s squared times theta c. So it's a relatively big angle. This theta c like 0.05, so this theta for the gluons, which are equal probability for the one, like 0.5. So most of them go directly outside the jet cone, and even if they don't themselves, they will rapidly branch again and again into softer and softer gluons, and eventually all the gluons produced by this democratic cascade go at large angle. So essentially all the energy which is taken by primary gluon, this energy of 4 omega branching, will go outside the jet and will contribute to the energy lost by the jet. So, and this energy will appear in many soft quanta by hitting at large angles, while many soft because of the democratic branching, which is produces gluon just softer and softer down to the scale given by the medium temperature, the thermal scale. And that's a picture that Jean-Paul, Yasin, and myself have developed a few years ago. I forgot the name. The reference is written, but I don't always read them as this. So that's a picture of the multiple democratic branching, which explains naturally why the energy lost by a very energetic jet is found in many soft quanta propagating at large angles. And that's a typical of the data which show this phenomenon. This shows the distribution of particles of the PT, what's called the jet random momentum profile. So the distribution of PT in angular separation delta R from the jet axis here. So delta R is increasing. When delta R is 0, we are on the jet axis. On delta R is about 0.4 in this case, we are at the edge of the jet, and when delta R is bigger than 0.4, we are outside the jet. And now if you look at particles in different annular rings, according to their PTs, one see that at large angles outside the jet, we have an excess in lead from proton for the particles which are relatively soft. In this case, it will be above 0.7 GeV. And this is precisely the phenomenon of digital symmetry. You see a large excess for the most central collision. This is like that. You see a large excess for the most central collision in the number of soft quanta at large angles way outside the jet axis. And essentially the distribution is flat angles because these particles, they can go to any angle because they thermalize. So,
should we think of the 5 GeV gluon emitter as doing the exact same thing?
No, because they never survive at 5 GeV.
No, but do they do the same democratic branching?
Yes, that's the point. So the gluon 5 GeV, they do democratically branch. That's why they never show up at 5 GeV, they show up at like 0.5 to 1 GeV. Without the democratic branching, we will not have this picture. You'll have maybe energy outside the jet, but slightly outside the jet. It will be easy to recover the energy. But because of the democratic branching, they go to very soft quanta, which can go to any angles, and then it's not possible to recover the energy. And if you don't recover it, blow it like that, the energy keeps going outside. And so this explains the digital symmetry, also explains the jet shape. That's one of the ways to calculate the jet shape. Good, but this does not explain what happens inside the cone. So how to understand, for instance, this data for the fragmentation function, especially how to understand the excess of soft particles, say around few GeV, 2 GeV or less, inside the jet cone at small angles. Now, this 2 GeV is more than 5 GeV of omega branching. So if there was medium-induced emissions, they should go outside the jet, but they don't. And I will try to explain to you what follows. In fact, these are vacuum-like emissions. That's why they're emitted directly outside of the cone. Sorry, outside of the medium. Sorry, they're inside the cone, but outside of the medium. Because of that, they don't suffer the momentum. So this means that there is an excess of soft vacuum-like radiation in lead-lead as compared to proton-proton collision, which means that vacuum-like radiation is also modified by them. That's what I like to explain to you. And in fact, this whole picture of the excess here and expression here can be explained by what I'm going to explain. So, now I would like to focus on vacuum-like emission and to explain to you why they're modified by the medium. And to make problem simpler, I will start with a jet, which is a quark anti-quark antenna with object angle theta QQ bar, relatively small, which is produced, say, by the decay of a color singlet object, a photon or a Z photon, which is boosted, so this angle is relatively small. And this antenna, is my jet, propagates through the medium over a distance L from the formation point up to the point where it exits the medium. And while propagating through the medium, it can radiate gluons, which are another one. Some of the gluon emissions have formation times more than L, this one and that one, so they're inside the medium. Some other emissions have formation time larger than L, so they're emitted outside. And what I said here, emissions, they're vacuum-like, so the formation time is 1 over omega theta squared, depends on energy and emission angle of the gluons. And for some of the emissions, the formation time should be more than L, for the other one should be bigger than L. And to distinguish that, I plot here the phase space omega theta in logarithmic units. So that's the phase space for the emissions. So in this phase space, energy goes like that up to value E, which is the energy of the leading particle. So in this case, E is energy of any of the quark on the anti-quark. I assume that have equal energy for simplicity. The angle, emission angle, is indeed like that. So theta is the angle between a total gluon and its parallel. So theta can be this one or that one or that one. Theta is increasing like that. I will show in a moment that theta can be at most theta QQ bar. In fact, by definition, if you're looking at radiation inside the jet, we only care about theta up to theta QQ bar. So the energy increases like that. The theta increases like that. This is a double logarithmic plot. So the line or the formation time is constant equal to L. So L equal to 1 over omega theta squared is represented by a straight line in this double logarithmic units. So this straight line here is the condition that omega theta squared is 1 over L. So formation time is equal to L. And all the points on the right of this line, which means having higher energies or higher angles, corresponds to formation time smaller than L. So this is a gluon emission which occurs inside the medium. Whereas all the emissions on the left of this line have formation time larger than L, so they're emissions which occur outside of the medium. And there is a limit on the emissions, on the transient of the emissions because of hydronization. The gluons or the quark, the partons cannot be softer than a scale given by lambda QCD. So the constraint that the transient momentum omega theta is of the lambda QCD marks the end of the partonic branching picture. Here we have hydronization that we're not going to describe. But in any case, this is another line in double logarithmic units with a different slope because omega theta is equal to omega theta squared. So this line omega theta equal lambda is a line which marks the end of the partonic branching. So we have partonic branches from here all the way to here. Part of the partonic branch for inside the medium, part outside the medium. They're all supposed to be vacuum lines, just standard branch. And here I stop the cascade and I count the number of partons. And then I have to maybe use a hybridization model to count the number of hadrons, but I'm not going to do that. I will only speak about fragmentation into partons. Now, I want to speak about vacuum-like radiation. I mentioned to you that the vacuum-like radiation has formation times. It's relatively hard. So it has formation times smaller than this particular value depending upon the energy of the gluon, which would be the formation time for medium-emitted radiation. So if I'm looking, so let me represent the constraint that the formation time 1 over omega theta squared is equal to this value, square of omega divided by Q. This equality defines a new line, which is inside the medium. And the formation times for the vacuum radiation should be shorter than that because should satisfy this constraint. So the vacuum radiation can only occur on the right on that line. So although this region, this white region here, is still inside the medium, inside this region, the formation time will be of the order of the medium-induced formation time, so the particle will be relatively soft. So I cannot have here any vacuum radiation. There is a Vito region between the line defined by medium-induced radiation and the line defined by the side of the medium, within which I have no vacuum radiation. I can have vacuum radiation inside the medium, but only on the right of this line, or I can have it outside the medium on that. And the veto region corresponds to formation times which are larger than the larger than the formation time for medium radiation and more than L. Because by definition, this cannot be vacuum-like. The vacuum-like has to satisfy that this is more than the scale, so if it is larger, it cannot be vacuum-like. So there is no vacuum-like radiation. Of course, there will be medium radiation. I'll do that in a moment. But if I only look at vacuum-like radiation, this region is forbidden. And this forbidden region ends up at the point which is the intersection between these two lines, and it's easy to go to this. So the square root of omega divided by z equal to L, and that by definition defines omega c. So this is omega c here, and the corresponding angle which follows from this to that is theta c. So this particular values omega c and theta c, which are included by the medium, represent the end point of the veto region. So to summarize, gluons within the veto region should have a transit momentum squared more than the Q hat time deformation time, which is impossible because they cannot have more than that. And so they cannot exist. The vacuum radiation has a veto region, and that region of exclusion in the phase space, it's a leading twist effect, because the radiation is still occurring according to the de Graaf function, but it just occurs in a limited phase. So that's the important effect of the medium on the vacuum emission. It excludes a part of the phase. To give you an idea, I put in some typical values for L and omega c. This L gives omega c over 550 GeV, which means omega branching for the 5 GeV I was saying before. And this angle here, theta c, like 0.05, is a very small angle. So typical angles like theta to bar here, like 0.4, 0.5. So there is a huge phase space between the scale and that oblique, angular oblique of the jet, within which I have the right vacuum radiation. Now, so let me describe a bit for you what is vacuum radiation, because as I just mentioned, emissions here occur exactly like in the vacuum. So let me remind you the picture of the vacuum-like radiation in the leading double logarithmic approximation, which relies on the standard formula for the Bremsstrahlung, for differential probability for Bremsstrahlung, which shows logarithmic enhancement for sub-radiation and for point radiation. When omega is more or theta is more, we have this energy logarithms times angular logarithms. And because of that, if you want to keep only those emissions which are enhanced simultaneously by energy log and angular log, we have to look at successive emissions which are strongly ordered both in energy and in angle. In fact, the fact that the energy is decreasing from one emission to another, it's obvious by energy conservation, and to have a large log, we need to have strong energy ordering. The fact that the angle must decrease from an emission to another one is ensured by color coherence. I will do that in a moment. That's a standard angular ordering feature of the vacuum cascade. And to have a logarithmic enhancement in angle, you have to have strong angular ordering, not just the angle should not just decrease, but should strongly decrease. So this angle might be bigger than this one, bigger than that one. Under these approximations, all these emissions are really easily summed. We have for n emission, where n can be anything, we have a factor alpha n times the logarithm to power n of the energy times the logarithm to the power n of the angular phase space times factor 1 over n factorial, because we will have to order them in successive emission in angle and in energy, another 1 over n factorial, because we have to order them in angles also. And in fact, this whole series, I didn't write it here, but this whole series is recognized as the power series expansion of a modified Bessel function. So the spectrum produced by say the leading particle here in the double approximation is simply a Bessel function. Okay, so I mentioned before the color coherence. This is important because you have taken this emission from antenna. So let me now explain to you what it means. So in vacuum, emissions at large angles, larger than the opening antenna and opening angle of the antenna, are suppressed by color coherence. Why? Because the gluon that would be emitted at large angles overlaps simultaneously with the quark and with the anti-quark, so it can be emitted either by the quark or by the anti-quark, and because it interacts equally with both of them, because it has produced a large angle, and because the quark and anti-quark have opposite color charges, the total emission amplitude is 0. So there is no way after angular, so there is no emission at large angles. That's the situation in the vacuum, but in the medium, the situation becomes more subtle. So now let me look at the same antenna with the same opening angle, but inside the medium. While propagating through the medium, the quark and the anti-quark scatter of the medium constituents, and this scattering is incoherent. So because of that, the quark and the anti-quark suffer independent color precessions, so they will lose their color coherence eventually. And it's easy to estimate when this happens. This happens when the transfer momentum squared acquired via collisions, which is 3 t in the time t, becomes of larger than the inverse transfer separation between the quark and the anti-quark squared. If you want if you take the inverse of that, the distance separation becomes larger than the transfer wavelengths acquired via momentum scattering, or via momentum broadness. And this transverse distance between the quark and the anti-quark for antenna of opening angle theta q bar grows linear with time, so we have theta q bar times t squared here should be one of the, or that should be smaller than q of t, and this gives the constraint that t should be larger than this particular scale. So when t is larger than this scale, which depends upon the medium property you have because of the scattering and upon the opening angle of the antenna, when t is larger than this scale, then the antenna becomes incoherent. The quark and the anti-quark are not color coherent with each other, so they could, in for instance, emit at large angles. So this, for instance, if I have to take the example of emission, that emission at large angles during the coherence time, at that time this quark and anti-quark are still coherent with each other, so this is forbidden. But at larger times, the quark and the anti-quark become independent, so the color here and the color there are independent from each other, so this gluon can be emitted at large angles, it doesn't really care about the anti-quark. And this particular coherence time that you find here is much more than L if the opening angle is much bigger than theta c. So it becomes of order L when theta q bar is for theta c. And since theta c is 0.05, I told you before, while theta q bar is much larger, like 0.5, we see that the typical situation that our antennas have angles bigger than theta c. I don't speak only about the original antenna, but also all the subsequent antennas here. So this whole physical phase space here has theta much bigger than theta c. Okay, so in this whole physical phase space, the antenna which are created by subsequent emissions lose their color coherence while propagating to the medium. So in principle, they could radiate a large angle. So this may lead to violation of the under ordering for the gluon vacuum-like emissions inside the medium. So that will make a difference with respect to the vacuum, because I said before that the vacuum-like emission in the medium could like in the vacuum, but in the vacuum they are under ordered by color coherence, whereas in the medium the antenna loses color coherence. The question is what happens in the angular ordering? And the short answer is that the angular ordering is nevertheless respected. Could be violated, but it is not. Why? Because the angular ordering is only relevant for emissions at large angles. But when the angle is large, the formation time is short. So if you want to have an emission which is vacuum-like and at large angles, have this formation time and has an angle bigger than theta q bar, then the associated formation times happens to be smaller than the coherence time. So wide angle emissions have formation time larger than the coherence time. So if you want to be at the same time vacuum-like and large angle, is necessarily emitted during this early time when the gluon, the quark and anti-quark were still coherent with each other. So then it is forbidden by color coherence, like before. At larger times, one can have emissions which are produced at small angles, but these are by definition incoherent because they don't overlap both on the quark and the anti-quark. So in other terms, the loss of color coherence by the antenna due to collision in the medium has no impact on the vacuum-like emissions. Emissions at small angles can be emitted at any time during the coherence time or after the coherence time, and emissions at larger angles could only be emitted during the coherence time, but they are forbidden by color coherence, so they don't occur. So this in medium antenna preserve angular ordering like a backline, and as a consequence, the vacuum-like cascade inside the medium are still strongly ordered in angles as they do in the vacuum. So at this moment, we have somehow the full argument telling that the cascades produced via Bremsstrahlung inside the medium are exactly the same as in the vacuum, except for having a smaller phase space, which is limited by this theory. Good. So far I have discussed emissions which are vacuum-like which occur inside the medium. So the formation times are smaller than L. They're ordered in energies and ordered in angles. The emission angle is decreasing. So I say I have these 3 points in the phase space: the first emission, the second emission, the third emission. At some point, of course, one cannot go from the point 3 inside the white region because that's vital, but the gluon with this kinematics can emit a gluon outside the region directly, so jumping over the vital region. For that to happen, the formation time of this additional gluon should be larger than L. With what I show here, so the gluon 3 can emit a gluon 4 outside of the area, outside of the medium, sorry, with energy below the vital region. What is important though is that before emitting this, because the formation time for this emission is large, it's supported L by construction, because one emit outside the medium, the antenna which is emitted the gluon has propagated to the medium over this one for the L. So it had a large time for propagation, so it was able to lose the coral coherence. So this antenna here, when it emits, has no coral coherence anymore, so it's not constrained by angular ordering anymore. So this particular antenna can emit at any angle, and here I have chosen on purpose to let it emit at an angle larger than the parent angle. So if you look at this cascade here, the angles decreasing inside the medium, but then the first emission outside the medium is produced by a gluon which propagated along to the medium. It has lost, this antenna lost coral coherence, and because of that, the gluon 4 can be emitted at an angle bigger than the gluon 3. After being emitted outside the medium, this gluon, the gluon 4, starts a cascade, which is angular ordered by the standard coral coherence antenna. So the first outside emission is not constrained by angular ordering. It can vary with angular ordering. And that's another important effect, which is again a leading twist effect. So there are 2 leading twist effects on the radiation due to the medium: the existence of the vital region, which suppresses a part of the phase space, and the lack of angular ordering for the first outside emission. And this is important because it reopens the space toward large angles. See, typically, an evolution inside the medium would like to go to angles as small as possible because that gives a strong logarithmic enhancement. But when it gets here at angles which are very small, if it was angular ordering, then we could only emit at angles which are even smaller. But without angular ordering, this first emission can occur anywhere inside, outside the medium at any angle, and then can generate cascades. Then the large phase space for angular cascade, angular order cascade. And that's this. I mean, all this picture can be easily put into mathematics. I think DLA level things are as simple in the medium as they were in the vacuum. So I don't give you details. I just show you here the double differential distribution, the number of gluons per unit of omega, per unit of theta squared times omega and theta squared, I call it T of omega and theta, as produced by an antenna of omega and theta cube bar, which propagates to the medium, with including an arbitrary number of emissions inside the medium with angular ordering, 1 emission without angular ordering outside the medium, followed by an arbitrary number of emissions outside the medium with angular ordering. And to compare the spectrum produced in this way inside the medium, I divide T by what I call T vacuum, which would be the cascade produced from here up to there without any medium. So there's no difference, there's no vital region, there's no lack of angular ordering. So by definition, there is no vacuum-like emissions in case of the medium inside the vital region. So the ratio here is 0. So T divided by T vacuum here is exactly 0. So this is the color code. Yeah, 0 should be black, not here. What is below 1 is red. What is suppression in the medium is red. What is above 1 is blue or yellow. This is enhancement in the medium. Now, this is theta C, which happens to be 0.06 for this particular value from here, and this is omega C, which is probably like 60 GeV if I remember properly. And now, if you look at the radiation inside the medium, there is no difference, but I told you before that what happens inside the medium, it's the same as in the vacuum. So the ratio is 1, and the white corresponds to 1. So this is exactly like in the medium of this region. And now, if you look outside the medium, there is a region where there is suppression with respect to the vacuum, and there is a region where there is enhancement with respect to the vacuum. The region where there is suppression corresponds essentially to angles of order theta C or smaller. And this is because we have less radiation toward this angle because we have less sources. We have no sources here. And because of that, there is less radiation as compared to the vacuum. The region where there is enhancement corresponds to angles theta bigger than theta C. Whereas compared to the vacuum, we can also emit from sources at smaller angles because of the lack of angular ordering. And that's particularly important if you go at very small angles, sorry, very large angles, close to the bar, where you have a strong enhancement, like a factor of 5 respect to the vacuum, because you can produce gluons here, not only from gluons with larger angles, but also from gluons with smaller angles. And that's open to phase. And this is the two-dimensional distribution in angles and energies. Now, if we integrate over angles for a given energy, so we integrate over this line at all the energies, then you find the fragmentation functions. Once again, I divide the fragmentation function in the intermediate by one in the vacuum, I show the ratio here. And we obtain these plots here for two different values of Q hat and L, the blue, the yellow, sorry, the red and black. And you see that they respect the pattern I showed you before. There's more suppression at intermediate energies, because these intermediate energies are here, and I integrate mostly to the red area. See that that's intermediate energies, so I integrate to the red area. Here there is no sense of difference, but here is less. Here not at all, here is less, so it's obviously suppressed. Whereas the lower energy corresponds to integrating over this area, and I see I integrate most of the region where there's an enhancement as compared to the red. So I get a strong enhancement. So the suppression of energy due to the fact that this phase space is reduced by the Victor region, and this amount of suppression increases with L into hat. So if you increase L into hat, you have more and more suppression because the width of the Victor region is increasing if you increase L into hat.
How come doubling Q hat makes a tiny difference between the red and the black?
Because the dependence upon the Victor region is only the value. Because it's a matter of changing the phase space. So it's only, you modify the corner here by a factor of 2, but you modify the phase space by a factor of log 8. That's all. So
that then tells me I can't measure Q hat.
Not in this way. But you can well, let me go on. I'll almost done. I'll show you probably better idea. As a matter of fact, these results here are a bit exaggerated, so that this enhancement is larger than one in the data. That's because we look at the double logarithmic approximation, which automatically amplifies the number of emitted gluons behind the correlative value because there's no energy conservation. Now, I modify.
Can I quickly ask? So, do you have any difference between quarks and gluons, or is that
not yet, because in the DLA we have gluons, but I will have it in a moment. I'll put all that in a Monte Carlo, and I also have the quarks. For the time being, I have only DLA, so the leading pattern can be anything. In this case, it's a pattern by pattern term. It could be anything, but the whole radiation of DLA is only gluons. I would not have this double log enhancement if I was emitting quarks. So just to emphasize that there was this qualitative, just qualitative similarity between the two plots. I have no enhancement at large PT. Again, it's a consequence of that I have no energy conservation. This enhancement here is a trivial consequence of energy conservation, and so the enhancement here is a trivial consequence of everything on the left here. If you have energy conservation, here I don't have energy conservation. And I have a significant enhancement at low energy due to the lack of angular ordering for the first emission outside the medium. And this enhancement is slowly increasing when you increase the jet energy. You see the peaking jet is increasing from the black to the red and to the blue. You can see in the data a small enhancement. I don't have the data for different energy, but the same pattern happens also in our case. Why? Because if you go to higher energy, you increase the phase space for the radiation. And the first one to propose this mechanism for enhancing radiation at large angles due to lack of angular ordering was in fact Iancu in Poland paper. Now, how to go behind the DLA approximation? First, I will still keep a format with only vacuum-like emission based on differential equation, like Big-Up equation, but I will make a better approximation than DLA. I will introduce running coupling. It depends on the transfer momentum of the emitted gluon, omega theta. And I will also add the finite part of the splitting function in an approximate way. So I still don't have energy conservation, but I have what is called the next to DLA effects. That's a common approximation. So I still have no energy conservation, but I have better splitting functions. And then the effects are seen here. So the black curve is strictly DLA. The red curve is DLA with running coupling, and the blue curve is this better approximation of the splitting function and the random coupling. You see that the qualitative features are preserved. There's still enhancement and suppression, but the amount of the enhancement is strongly decreasing. Also, to emphasize the role of the color, the coherence, I show here two plots, both obtained with a more advanced approximation, with this next to VLA approximation with random coupling. The one here is the same line as here. So I have the violation of angular ordering for the first initial outside the medium, while the one here forgets about this violation. So assume that angular ordering is preserved throughout the whole cascade, including the first initial outside the medium. And of course, then I do not open the phase space at large angles, and indeed I have no enhancement one.
So the effect is the effect of the Vitor region?
No, it's the effect. It's the effect. So the difference between that is just the angular point. The lack of angular. Sorry, the lack of violating the angular ordering. So I just assumed, yeah, the Vitor is the same in both cases.
No, but the second,
the ratio is a ratio to the vacuum, and so the fact that that's suppressed in even without decoherence, the fact that that's suppressed, I guess, is the Vitor region.
The suppression is the Vitor region, but the fact that here I have no enhancement
Absolutely.
is a lack of angular ordering.
Absolutely.
I mean, it's a strict. In this
there's
case,
still a medium effect.
Yeah.
Right? Even if you remove decoherence, right?
exactly. Even with the coherence, you have the Vitor is still there because the Vitor region is still there. But since you enforce strict angular ordering, you do not allow the first initial outside the jet to outside the middle to go anywhere, and then you don't open the phase space for initial of larger angles. You don't see any. And so, and then what you have done.
I have a question also regarding that. So earlier, I thought you said there's one emission that violates angular order. It's a huge effect.
Yes, because this is what happens. The most of the after the emissions, the evolution inside the medium goes naturally towards more and more angle because it has a big loss.
Sure.
So most of the particle will be here at theta of order 0.05.
And the reason it's so big is because the denominator is small.
Yes, and then if you don't allow them to radiate at large angles, they can only radiate at even smaller angles. But by allowing the particles, so see, there is a huge difference. If you look at how can you create gluons here, if there was strict angular ordering, you can only create a gluon here from gluons at even larger angles, but which are very few. But now most of the gluons are here, and now they can readily there.
So one chance makes a huge difference.
Exactly. And the most advanced way to take this picture into account, which is something that we are about to write a paper now, is to implement this whole picture into Monte Carlo. It's a probabilistic picture, so it's amenable to Monte Carlo calculation. And we have already preliminary results, I'll show you in a moment. So in this case, in this way, we can also implement exact energy conservation by using full splitting functions, and also implement the energy loss via medium maneuver radiation. So the whole physics in this factorized picture is there. So the Monte Carlo is based on a convolution of 3 showers, vacuum cascade inside the medium, but outside the Vitor region, which contain just a full splitting function, running coupling, quarks and gluons with quite splitting functions and NC. Then once I create these gluons inside the medium, then I allow them to produce medium-induced radiation, to act as sources for medium-induced radiation. This again can be treated by a Monte Carlo. So I create what's called the medium-induced cascades with democratic branching. In this case, we fix the coupling for technical reasons, but the coupling is more or less fixed in that case. I can argue why. So it's less important because there's no strong order in gay part anymore. It's democratic, so the coupling more or less fixed. And this medium-induced cascade bring energy loss and transit momentum browning. In particular, partons can acquire angles bigger than theta 0, the angle opening of the jet. In that case, they leave the jet. So this contributes to energy loss by the jet. But the partons which remain inside the jet, so all the partons which remain inside the jet, which be the vacuum-like or medium-induced, can act as sources for vacuum-like emission outside the medium. In particular, the first emission outside the medium has no angular ordering, and this can happen even for sources which are medium-induced, not only for vacuum-like. And this gives rise to vacuum cascade outside the medium, which start at larger angles because of this lack of angular ordering here. And this cascade is top of quite angular inversion line. And when we simulate this whole process by the Monte Carlo, we start with a leading particle, which is not with a fixed energy, but which is taken with a probability given by the cross section for a hard process, in this case, proton-proton, two partons scattering at energy 5 TeV, that's taken from Vidya. So this way we give the bias of the physics exactly as in the experiment, where the fact that the cross section for the hard process decreases very rapidly with increasing the jet PT biases the whole process towards events with the smallest possible energy loss. And that's important because this is what makes this whole scheme of energy loss be dominated by the energy losses as small as possible, which means of the order of typical scale, which was omega branching, which is alpha squared omega c, rather than the average one. The average one will be bigger than that, but it is irrelevant because it is washed out by the bias coming from the hard process. Okay, so all that is the ingredients. These are the results. I have here several results, and let me comment on them separately because I just showed what I mean. So first of all, I focus on two observables. So these are the spectra. The spectra, the blue line is the spectrum in the vacuum, and all the other line are spectra produced by vacuum like medium-induced by in the medium for full radiation with different values of Q hat and L, and alpha S, which is fixed for the medium induced radiation, but otherwise it's given by the running coupling for the vacuum cascade. And using this spectra from here, we have computed two quantities, two observables. RAA, which is shown here, for this whole set of, for the blue line is 1 by definition, and for the other variables, Q and L, it's more than 1, and it's slowly increasing with the TTJ, or like in the data. And we also show the ratio of the fragmentation function in lead divided by proton-proton. And for all this, you see that the suppression at inhibited energies is only slowly modifying because the value of Q and L is slowly changing, and but the enhancement at low energy is more strongly dependent on that. And now we also see the enhancement at high energy, or a large Z fraction, because we have energy conservation. And now because in our process different mechanisms are parameterized differently and factorized differently, we can easily tune them off and on to understand what's the physics there. So I have here different scenarios: no quenching, no decoherence, quenching before backlight emission. What they mean? No quenching means that in this Monte Carlo we decouple the medium radiation. We have only vacuum-like emission inside the medium or outside the medium. And of course, in that case, so that's a black dotted line. In that case, there is no energy loss. If you do that RAA, it's just part of that definition. It's dotted here. On the other hand, the suppression in the fragmentation file. Sorry. Yeah. If you look now at the dotted line again, at the fragmentation function, you see that instead of having an enhancement at more energy, now we have a suppression. So, in introducing energy conservation, reduce the number of sources, and the mechanism which was nicely operating at double whammy approximation is not operating anymore without medium radiation. But on the other hand, of course, as I mentioned to you before, the full result has enhancement here, and this is associated with medium-induced radiation. So let me comment on that. So, the red curve is a total result which contains emissions outside the medium at any angle from both vacuum-like and medium-induced sources. And this was only vacuum-like, and this vacuum-like plus medium-induced. This clearly shows that there are a lot of medium-induced sources which can radiate at large angle, which are responsible for the enhancement at molecule. And to emphasize that even better, we decoupled color decoherence, so the dotted green line, which means that in this case there is strict angular ordering all the way along the cascade, including for the first outside emission. And then there is the enhancement at more energy is much more, because in that case we don't have such much phase space. And finally, what we call quenching before vacuum-like emission means that we have no vacuum-like emission inside the medium. So we have just the leading particle, which loses energy, have medium-induced cascade, and then it branches outside the medium. In that case, it loses much less energy, so RAA is much larger, because what loses energy here is just the leading particle, while in general, we have the leading particle plus all the other vacuum-like partons, which all lose energy separately. And also in this case, the energy, the RAA increases faster with PT jet, because there is no this effect of having more and more particles within the jet. There is no evolution by definition inside it. So get artificially cut off. Okay, so the conclusion of all this kind of test is that partons created inside the medium via medium-induced emissions significantly contribute to the soft radiation outside the medium. The difference in that line And that's my conclusion. I won't do them again because I already emphasized them already over time. Thank you.
Questions, but they go from left to right.
Okay. So you said the reason for the enhancement at large in the fragmentation is from energy or momentum conservation, but I mean, isn't it really just the fact that you bias your initial distribution of tests to be different?
Of course, it's the same.
So that's what you call momentum conservation.
Well, it's, yeah,
Because you force them to be at least 200 GeV, right? So you have a different set of jets in the vacuum.
So there's a difference between the energy loss by one parton and the energy loss by the jet. The fact that the energy loss by the jet is larger than energy loss by the parton makes that the ratio, makes that the parton that we measure as a given Z in the medium case come from parton with a larger Z in the vacuum case. And parton with a larger, sorry, with a smaller, with a sub one, I said with sorry. And parton with a smaller Z have a larger probability to exist. Right? So
but yeah, so you're biasing your initial distribution before medium evolution to be different. Right?
Yes, but energy conservation is important. Why? Because you want to keep. If there was so, the energy conservation is important. The fact when you have PLA, you don't keep trace of the fact that the leading particle has lost any energy. So if it did lose energy, you count the radiation, but you count with the same value of Z as before. So this whole physics that we just discussed is missing there by definition. So in that sense, energy conservation is important.
Sort of an additional.
Well, it's not just energy conservation. It's the imbalance between the energy lost by one parton and energy lost by the jet as a whole. The fact that the energy lost by the jet, right? So because we have, well, this is right now. That's very interesting. So let's look at the jet as a Z. We look at the same value of jet of Z for jet in the vacuum, jet in the medium. Compare, but the energy. So E is the same. Is the same for the jet in the medium and the jet in the vacuum. So this Z is omega over E for the jet in the vacuum. But for the jet in the medium, this omega was some other omega 0 minus delta minus energy loss delta, we call it epsilon, divided by energy which was E0 minus delta E. So to have the same Z in the final measure parton with the final jet with a given E, I have to start with a jet with a higher energy 0 and with a parton with a higher omega 0. Now this delta E is typically n times epsilon, where n is a number of partons in a given event, in a given jet. And so this delta E is typically bigger than epsilon. And that's important because now I can, and both epsilon is much more than omega 0, and delta E is much more than E0. So I can expand that out, and it gives omega 0 divided by E0 minus epsilon minus omega 0 divided by E0 times delta A E divided by E0. So this is Z0.
Omega 0. On the right hand side, it should be epsilon over omega 0 if you're.
Sorry.
It's minus epsilon over omega 0 plus delta E over E0.
1 minus.
Yeah, that's right. It's 1 over E0 times 1 plus delta E divided by E0. All that times minus. So I have, yes, I have omega 0. Yes, omega 0 divided by E0 times delta E over E0, right? So plus, no, plus, and minus E. I'm getting that. Precisely. And because, you see, this is Z0. So this is Z0 plus Z0 times delta E divided by E0 minus epsilon divided by E0. And now, we're looking at particles that we large Z. So this is also for the 1. So this is for the 1 as well, but delta E is bigger than epsilon. So this is bigger than that, it's positive. So Z, yes, Z is bigger than Z0. It might mean that the gluon that we measure with the given Z in the final jet, in a final jet, used to be produced with the Z0 smaller than Z. So you always produce a larger probability. So that's why there's an enhancement. This argument goes backwards if Z0 much more than 1. But then the delta A is the number for the, I don't know, a few patterns, like 5 patterns. So Z0 is 10 to minus 2. Obviously, this is more than that. So this argument would predict a suppression at more than 0. And indeed, that's a suppression we see at intermediate values of Z0. But at very small Z0, you see the lack of unordering.
Sorry, E0 isn't like
E0
times omega 0?
Yes, it is.
So the ratios are equal, and Z0 is smaller than 1. So the term overall is negative, right?
No, E0 is the same, both here. It's E0.
Oh, this is E0.
So it comes from here. I don't expand that one. Right? So the less term is minus epsilon, but this is much more than that, so I expand that up. The less term here, just epsilon divided by 0.
Okay, all right, so now I see, okay.
So Z0 is for the 1, for the 1, right? So, but indeed, this argument also explains to some extent the suppression and intermediate values of
I have a much shorter question.
My question was short.
I have a question which I'm sure has a much shorter answer, and the answer is yes. Can you then run your Monte Carlo instead of for 200 jets, for jets that are 20 to 30 jets? Because that's the range that we'll be looking at in EIC, and that's also the range that one can look at in SPs.
Yes, second.
Because I think that prediction would be important because it would tell us, it would allow us to check in SPhoenix that the whole machinery actually works, and it would allow us to figure out just how precise we have to make the measurement.
We have to see a bit more about the value of the factorization for lower energy jets, but that's possible.
Yeah, it probably shouldn't be too bad because this whole discussion was developed for jets and Petra. This angular ordinate, et cetera, that went into the Herwig Monte Carlo, which was developed for Petra jets, and that's more or less the same region with the Petra region. So it wouldn't be quite so good as in this region that has been described, but it shouldn't be crazy.
That'd be very valuable.
But presumably at the IC there will be some advantage that the medium would be static and just the nucleus,
Yeah, the medium would be much more.
It's right, it's a cold medium. Yeah.
So in a way,
you're not going to see it.
Well, this is an AIC program, so the question is what can the AIC do to help them understand?
so yeah, so the main difference will be less than. So the main difference will not be the fact that the energy of the jet is much more than 200. The main difference will be that you have it much more. You have instead of being for the 1, like 0.1.
Oh, 1 over 25 is
0.0.
Okay, so you're saying it's all completely irrelevant for AIC?
No, it's not completely irrelevant. For instance,
it should be studied. It should be studied.
For instance, for additive corrections to Q hat, I mean, you should expect similar corrections to QS. This is something that see the overlap between the.
Yeah, the high energy evolution.
So let me ask.
Yeah.
Let me ask a question this way. So this program will have a write-up, sort of a proceedings document based on everything that we're doing every week. Emphasis in physics, which we did since the
I hope you have a good time doing that right now.
So, is it possible to run the Monte Carlo for EIC type of parameters just to get a ballpark for this write-up, for instance?
Well, I think the more complicated issue is the kinematics. See, everybody was starting out with the kinematics of a heavy ion collision with the jets are clearly produced in the medium. Now you've got a kinematics where, at least if you're measuring the jets kind of forward direction, the jets are
produced outside.
Yeah. But, I mean, presumably if there are jets outside of the forward direction, you can measure them.
Yeah. So one would have to go through the kinematics.
Yeah.
I'm not sure that's going to be in the Monte Carlo.
No, it's not like it is. Yeah, we cannot just change parameters. We have to think about it.
Okay, so you need to write a new Monte Carlo.
I don't know.
Talk to Gregory.
Once you understand how it is.
Okay, one of you guys.
You can guess which of us guys is going to write this.
But I mean, the first step is to do it in PA conversions and what to do it in PA conversions separate. And then your kinematics.
Yeah, the problem is exactly the same. I mean, the conceptual issue It's about
Yeah, that's right. The Q max is the same for PA.
okay.
It's just that Q hat will be much smaller. But for EA collisions, it's a different kinematics.
Your question wasn't that short after all.
Sorry. I have the answer is yes, with more stuff.
Yeah, about like a 20-minute break and then the second talk.
Okay, so when do we return? Give people time.
Oh, let's say 11:30. That should be good. No?
15.
11:30.
Let's do 11:25.
24 and 30 seconds.
We may not have the room well after 12:30, but maybe we could. Okay, so let's make it 11:30. I'll check.
Yeah, let's check the room.
Okay.
Thanks to Edmund.